This program is brought to you by Stanford University. Please visit us at stanford.edu.
What we're talking about for the next, well, several weeks in any case, are the structure of the laws of physics, period. The laws of physics all have a common theme to them, a common, I shouldn't say an underlying basis, but a common form, the laws of physics. First of all, I should say what I mean by the laws of physics. There are some laws which are mathematical laws. 1 + 1 is 2. I don't regard that particularly as a law of physics. There are laws of probability theory. Right? The fact that probability works altogether may be a law of physics, I'm not sure, but I don't regard the laws of probability theory as laws of physics. You know, they're not specific laws of physics. All of the laws of physics, such as F = ma, such as the laws of motion of a particle in a gravitational field, the laws of electricity and magnetism, the laws of charged particles moving in electric and magnetic fields, all these classical laws of physics, just a collision of billiard balls, any such things, all of those laws of physics have a common form, and the common form is the principle of least action. The laws of thermodynamics, for example, which are usually not phrased in the form of mechanical laws involving a principle of least action, the laws of thermodynamics are simply the statistical laws of large numbers of degrees of freedom, given that the basic laws of those degrees of freedom have the form of the principle of least action. The second law of thermodynamics is partly a law about probability, and partly a law, a sort of meta-law, whose underlying nature it is that the laws of physics derive from a principle of least action. So we're going to be talking again today about the principle of least action. But before I do, as is my habit, I will talk a little, just some very elementary mathematical rules. When I said that I expected you to know some calculus, or at least at minimum to having remembered at least at one time have known some calculus, I also decided that I would teach as I went along all the basic mathematics that's really needed beyond the most elementary things. So what we're going to need tonight are two little theorems. The first theorem is the theorem of integration by parts. Most of you probably know about integration by parts, but since it's something we will use, I will derive it. First of all, suppose you have some integral, and let's make the independent variable be t, dt. It goes from t1 to t2, some function, but the function itself happens to be the derivative of some other function. df, or just ordinary derivative will do here. We don't need it to be partial derivative. df by dt. What is this integral? The integral of a derivative is simply the function back again, f. But that's the indefinite integral. The indefinite integral of a derivative is just the function itself. But the definite integral from t1 to t2, from t1 to t2 of a derivative is just the difference of the function f at the two endpoints of integration. It's equal to f at t2 minus f at t1. The easiest way to see this is just to think about what the integral of a function is. It's the sum of little incremental values of the function. But the incremental values, what does the derivative mean? The derivative just means the difference of the function at neighboring points. So this might be f at point 2 minus f at point 1 divided by a little incremental dt. And then the next interval is plus f at point 3 minus f at point 2 plus f at point 4 minus f at point 3, and so forth. Everything cancels out except the first and last term, f at 2 cancels out, f of 3 cancels out. They all cancel out except the last one and the first one. And so the integral of a derivative is just the difference of the function at the endpoints of the integration. That's number 1. Now, step number 2. Let's suppose the function f is actually the product of two functions. F is equal to the product of little f of t times g of t. Of course, every function can be written as a product of some functions, but let's be specific. Capital F is the product of little f of t and g of t. Now, what is the derivative of f with respect to t? It's the sum of two terms. So let's write that as f dot, meaning derivative, is equal to f dot, little f dot of t, times g, plus f of t times g dot of t. This is the rule for taking the derivative of a product. Derivative of a first factor times the second, plus the derivative of the second factor times the first. So let's apply that rule up there. F dot just means the f dt. And what it tells us is that the integral from t1 to t2 of f dot g plus fg dot. Notice the structure of the two terms. One of them is a derivative times a thing which is not differentiated, and the other is the opposite structure where the second term is differentiated, the first term is not. Well, according to the top line, that's equal to the product fg at one endpoint minus fg at the other endpoint. Let's make a notation for this. The standard notation for this difference is just to write f of t, t2, t1. That's the standard notation for the difference of a function at two endpoints. So we can write that this is the difference of a function at the two endpoints, the difference of the product of the functions at the two endpoints. Oops, t1, t2, and t1. Now, yes?
One thing in here that I haven't seen before is, I thought this would be true for the integral of df dt. The extra dt in there, I haven't seen before.
The integral of df dt.
Yeah.
Whenever you write an integral, there always has to be a d something. The f dt is just a function.
All right, never mind.
Good.
Stupid question.
Some people might.
I won't comment on whether it was a stupid question or not, but I will say, please ask me questions like that. You know, when you get a little confused about something like that, just stop me, slow me down, ask me the question, and force me to make things explicit.
You want to put a dt in the integral there?
In this one here, this is the one you're talking about, right? Yeah. So there should be a dt in that one. Okay. All right, now let's take a special case. The special situation is where either f or g vanishes is equal to 0 at the endpoints. That's a special case which will come up time and time again, where for one reason or another, either f or g is equal to 0 at the two endpoints. It could be f being 0 at both endpoints, it could be g being 0 at both endpoints, or it could be some mixed case. But in any case, if f or g vanishes at the endpoints, then this is just 0. So,
Or if the product is
Say it again?
at the endpoints.
say it again?
As long as the product is the same at the endpoints.
Even that's good enough. Even that's good enough. But in the special cases we'll be doing, as a rule, one of these two will always be 0, and so that's not there. All right, then we can write this formula in the form that is usually the integration by parts formula. The integral And now I won't bother writing the endpoints. The endpoints are implicit. I'll just, let me write them. T1 to T2 dt of f dot g. Now let me transpose this over to the other side. That's equal to minus the integral, same integral from T1 to T2 dt g dot f. So you see, if you happen to have an integral with the integrand, the thing you're integrating, happening to be a product of a derivative times another function, you can interchange which one is differentiated and which one is not differentiated, but at the expense of a sign. You have to change the sign when you change the place where the dot goes. Again, that only is true if the product fg, well, I was going to say if the product fg is equal to 0 at the endpoints, as long as the difference is 0 at the endpoints. But that's a fine point. So this is one small theorem. Another small theorem, it's an even smaller theorem. It's hardly worth calling a theorem. I'll expose the integration by parts again when we need it. Another little piece of mathematics. This one is so trivial that it's hardly worth even mentioning, but I'm going to mention it anyway. Supposing I have a function, let me call it a of t. And here's what I know about a of t. I know that when it's integrated, let's suppose it's defined again on an interval from t1 to t2. A of t is some function on the interval. Here's what I know about it. I know about that when it's integrated with any function, any other function, f of t, when you multiply it by any function of t, this can be any function. If you take any function, multiply it by a of t, and integrate it, let's suppose that we know that the answer is 0. That's a lot to know, that no matter what function you put here, if you multiply it by a and you integrate it, you get 0. What does that tell you about a? It tells you that a is 0. And the easy way to see that is say, if it's true for any function, let's check that a of t has to be 0 at some specific point. Let's take this specific point over here. Then all we have to do is to take a function f of t, which is 0 everywhere except in the vicinity of that little point. Then when we multiply the function a by this little blip, let's call it the blip function, when we multiply it by the blip function, we of course get something proportional to a at that point. And so what we'll get is something proportional to a at the point where the blip function is non-zero. Well, by choosing the blip function to be anywheres, we then prove that a of t has to be 0 everywheres. So if we have a function which when multiplied by an arbitrary function, the integral is always 0, then that function a must be 0, exactly 0. This implies that a is 0. Now you can't check this by integrating it with a specific function. If you just take some particular function and you do the integral and find it 0, that only tells you a limited amount of information. But if you could prove, now how long does it take you to integrate it with every possible function? Forever. So this is not something you do by hand.
That's not long enough.
That's probably not long enough. So as a rule, you don't actually check this by going through a family of functions. You prove that a of t times f of t always integrates to 0. Okay, now we're ready for the big one. The big one is the relationship between the principle of least action which is a global statement. Let me say what I mean by a global statement. What we're interested in is trajectories, or histories, if you like. Histories of systems. The system is described by a set of coordinates that we can call Q, Q1, Q2, and so forth. And the trajectory, or the history of the system, is a trajectory as a function of time. Time I take to be upward. Here I took time to be horizontal. I apologize for that, but the problem is that in elementary mathematics, the independent variable is always taken to be along the horizontal axis. In physics, the independent variable, which is usually of time, is always taken to be the vertical axis. So we have to tilt our heads every now and then to see it in perspective. Okay, so that's T. And a trajectory, or a history of a system, is a trajectory as a function of T of all of the Q's, the Q's being the coordinates. In other words, it's a set of functions Q1 of T, Q2 of T, Q3 of T, all of the various generalized coordinates that describe the system. If you know them as a function of time, then you know the history. We're interested in the histories of systems, the trajectories. There's two ways of going about formulating the laws of physics. One I will call local. Local means you concentrate on a location along the trajectory and you construct a law which tells you how to go forward at each point. In other words, given a bit of information somewhere along the trajectory, it tells you how to go a little bit forward. F equals ma is an example. It tells you the acceleration in terms of the position. So in that case, you need to know, what do you need to know in that case? You need to know the Q's and the Q dots. And if you know the Q's and the Q dots, then F equals ma will take you to the next point, and the next point, and the next point, and will eventually build up the whole trajectory for you. F equals ma I call a local law of physics. Local in the sense that it makes reference only to a little bit of the trajectory, a differentially small amount of the trajectory. The other way of describing the laws of physics is through a global, I'll call this global, a global formulation, which looks at the whole trajectory and says there's some quantity called the action, which is dependent on the entire trajectory, which is minimized for the true trajectory. For the true trajectory, the one that actually describes the system, the action is minimized, and for that, all you have to give, again, two endpoints. How many things you have to know? You have to know two things for each coordinate, the Q and the Q dot. Again, you need to know two things for each Q. You need to know Q at the beginning of the trajectory, and you need to know Q at the end of the trajectory. These are two different formulations of the laws of physics. And they are related. In fact, they're not only related, they are equivalent to each other if properly formulated. Now, how do you see that a global law, like the principle of least action, is related to a local law? And it's not very hard. You just focus in on a little piece of the trajectory here, focus in on a little piece of the trajectory, and say, all right, if I know the trajectory has gone through this point, and if I know that it's gone through that point, let's suppose I do know that it went through these 2 points, then the principle of least action tells me that it must go along a trajectory between these 2 points which minimizes the action between these 2 points. In other words, if it minimizes the entire action, it must also minimize the action locally between 2 neighboring points. Because if you chose a trajectory in here which didn't minimize the action between these 2 points, then it also wouldn't minimize the total action. So there is a relationship between the global laws and the local laws. In particular, if I give you the law of physics in the form of a least action principle, we should be able to derive from it a differential equation which describes an analogous to F equals ma. That's what I want to do now. All right, there's a few steps involved. And it's probably the hardest definition of derivation that we will have had up till now, but it's not very hard. All right, what I'm going to do is I'm going to take, let's call Q of t. Q of t stands for the actual trajectory that the system really takes, the solution for the problem. And it's not just one Q of t, it's Q1 of t, dot, 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 up to Qn of t, where n represents the total number of coordinates that it takes to describe the system. If it's a system of particles, then n is 3 times the number of particles. So that's our trajectory, and it's represented by this red line here. Now, let's change the trajectory a little bit, deform it a little bit, move it a little bit, by taking each Qi of t and adding to it a number alpha, alpha can be any number, times a specific f sub I of t. Let's invent a set of functions, arbitrary set of functions, doesn't matter what they are. Let's invent an arbitrary set of functions, f sub I of t, again, n of them, and let's add them to q sub I of t with a coefficient alpha. We're going to change alpha, but this f of I of t could be anything. What happens to the trajectory? Oh, and one other point. We're going to require that the trajectory passes through the initial point and the final point. That means that fi of t should be 0 at the initial point and the final points. Right? So fi of t is to vanish at the initial point and the final point. Well, I've erased it, but you can get the drift. Something is vanishing at the initial point and the final point. So we can write that. Fi of t, fi equals 0 at t1 and at t2. What does the trajectory look like if we shift it a little bit? Well, it'll be shifted. That's what will happen. It'll be shifted at each point t. It'll be shifted a little bit by an amount which is proportional to alpha, but also proportional to the set of functions fi of t. So it's a little bit of a shift of the trajectory. I've drawn it as though it was just a shift to the right. It's not a shift to the right. It's a shift in some more complicated set of directions, depending on the fi of t. Each of the fi's is shifted a little bit by an amount proportional to alpha. That gives us a new trajectory, not a fake trajectory, but a trajectory which is not a solution of the equations. Right? Let's calculate the action of the original true trajectory and let's call it the action of a true trajectory, A of the q's. When I shift the q's a little bit, A becomes a function of alpha. Why? Because the new trajectory depends on alpha, and in general, whatever the action is, it will depend on the trajectory. So A becomes a function of alpha. Let's forget the fact that it's a function of q. It becomes a function of alpha. For a given problem, with a given true trajectory and a given set of f sub i's, A is just a function of alpha. It's a function of the amount that you shifted the trajectory. The amount can be positive, it can be negative. If a positive shift of alpha shifts the trajectory to the right, then a negative shift of alpha shifts the trajectory to the left. Well, let's suppose we know that the action is minimized for the true trajectory. The true trajectory corresponds to alpha equals 0. That's unshifted, completely unshifted. The true trajectory is alpha equals 0. It says that A of alpha is minimized at alpha equals 0. That's what the principle of least action says. In fact, it says it for every possible collection of functions fi. No matter how you deform the trajectory, if the true trajectory is the minimum of the action, it says that for any f's, a of alpha will be minimized when alpha is equal to 0. That says, in turn, that the derivative of a with respect to alpha is equal to 0 when alpha is equal to 0. For alpha equals 0. It says any change in the trajectory parameterized by an alpha increases the action, and so that tells us that a is stationary at alpha equals 0. Now, if that's not clear, stop me and I'll explain it a little more. But this is one of the central.
Is there a separate definition for the action?
We're going to talk. Yeah, I thought I talked about it a little bit last time, but I'm going to come back to it now. Yeah.
A little bit.
Yeah, right. So let's now talk about, so far all I've said is, suppose there's a thing called the action which is minimized for the true trajectory. Now, what is this thing that we call action? It must somehow be connected to Newton's equations, because after all, the content is supposed to be the same as Newton's equations. Well, I'll tell you what it is right now. The action is an integral along the trajectory, an integral dt, from t1, from the starting point, t1, to the end point, t2, of a thing that's called L. L stands for Lagrangian. Lagrangian was named for Lagrange. Lagrange was, of course, a Frenchman, I think. Must have been a Frenchman. Lagrange.
He was Italian.
He was Italian, okay. Ah. Oh, no. He was Armenian. That's why they called it the Lagrangian. Was he really Italian?
Yes.
Oh, okay.
Born in Italy, I think, but.
Okay.
Right.
I thought he was
Yeah, the
French.
French claim him, and the Italians claim him.
Oh, okay. So he was like Napoleon. He sure, like Napoleon. Well, he was Corsican, but.
Well, Columbus,
Oh, Columbus, yeah. No. Nobody ever said Columbus was French. L for Lagrangian. And what does the Lagrangian depend on? It depends on the things that determine the trajectory. It depends on Q of t, all of them, Q sub I of t. Let's just call it Q of t, which means all of the Q's of t, but also the velocities. The position at every time and the velocity at every time, Q dot of t. So here, this, I haven't told you what the Lagrangian is in specific terms yet, have I? I actually have the last time. I'll just remind you, it is equal to the kinetic energy minus the potential energy. The kinetic energy typically is a function of velocities. The potential energy is usually a function of positions. So L will be equal to this, but we'll check that. For the moment, L could be any function of position and velocity. And the action is the integral. In other words, it's the sum all along the trajectory of little incremental actions from one point to the next. Little incremental actions which depend on the position and velocity along here, along here, along here, and so forth. You add them all up, and that's the total action, by definition. So far, I'm not even going to use the fact that it's t minus u. I'm just going to leave it to be any function of q and q dot. Okay. The question is, how do we find the trajectory which minimizes its action? This is a problem in the calculus of variations. It's a problem that's called the calculus of variations. Why is it called what's being varied? What's being varied is the trajectory. We change the trajectory a little bit, and we require that the true trajectory is the one which gives us the least action. All right, so this is the action, and of course it does depend on alpha because q depends on alpha. In fact, let's calculate, let's write out one or two equations over here first. What's the derivative? Here's let's write it this way. Q sub I is equal, now let me put a little symbol over this, a little hat. This indicates that this is the true solution to the mathematical problem of finding the correct trajectory. So let's call one of these trajectories Q with a little hat. I just put the little hat on it to indicate that it is the true trajectory. The hat indicates we've solved the problem. Then we add a little bit to the true trajectory, alpha f of t, and that gives us something that I'll call Q without a hat on top of it. We could even think of Q as a function of alpha. It is a function of alpha. Q at any instant of time is a function of alpha because it depends on alpha. Now what's the derivative of Q sub I with respect to alpha? It's just an ordinary derivative. I don't need to write partial derivative. The derivative of Q sub I with respect to alpha. Well, we'll just look at this. This doesn't depend on alpha. This does depend on alpha. So the derivative of Q sub I with respect to alpha is just f sub I of t. The change in Q when you change alpha is just fi of t. What about the change in the velocity? How does the velocity change when you change alpha a little bit? Well, the change in the velocity, the change in Q dot, if you shift alpha, is just f dot. Right? We can write down here Q dot is equal to Q hat dot plus alpha f dot. I'm assuming, incidentally, that alpha is just a number. Right? It's just a number, it doesn't depend on time. It's just a fixed number. Fix it once and for all. And then we're going to study the answer as a function of that number. The change in Q dot when we change alpha is just f dot. All right, so the change in Q with respect to alpha is f, and the change in Q dot with respect to alpha is just f dot. Let's find out now how much the action changes. How much does the action change when you vary alpha a little bit? Let's just differentiate it, dA by d alpha. Keep in mind what an integral means. It just means a sum of terms. It just stands for a sum along the trajectory. So integral, dt, none of these things depend on alpha. The thing that depends on alpha is the Q and the Q dots. Right? So how do we find out how much the action changes? Well, the integral, that's still there. The Lagrangian will change a little bit because the Q's and the Q dots change. For example, the Lagrangian changes because Q changes, Q sub I. The change in the Lagrangian when you change Q sub I times the change in Q sub I when you change alpha. So that's f sub I of t. This is the change in the Lagrangian due to a small change in Q times the change in Q when you change alpha. But that's not all there is to it. L also depends on Q dot. Right? So we have to add to it the change in the Lagrangian when Q dot changes times the change in Q dot, which is f dot of alpha, which is f dot of t. This is the change in the action when you change alpha a little bit.
You want to sum up I there?
Yeah, you want to sum over I. Thank you. All I've used is that the change in an object is equal to the change in each one of its arguments times the change in the argument. Okay? Summed over all of the arguments. Arguments meaning the sense of the independent and the independent variables. All right, so that's a little exercise. This you should be able to, looks a little bit complicated, but it's actually not very complicated. We just differentiated each one of the things inside L and multiplied by the amount that that thing changes. Okay, now, here we have a term that has an f of t in it. Remember, f of t could be any function at all with one restriction, that it vanishes at the endpoints. Remember, we're not allowed to move the endpoints. The endpoints are nailed in place. All right? But here we have f dot. I really would much prefer to have f there. Then I would have both of these terms multiplying an arbitrary function. All right? What's the trick to turn this into f?
Yeah.
Integration by parts. You can take the one which is differentiated, and undifferentiate it. If you take the one which is undifferentiated and differentiate it. All right? But you also have to change the sign. So let's just work on this. I won't bother rewriting it. Let's just work on it. We're going to undifferentiate this f at the cost of differentiating this whole thing here. I think I'd be best off to rewrite it.
Well,
Okay.
instead,
Hmm?
you know, you've got this G dot, I mean,
Yes?
do substitution.
I'm going to. What is G? First of all, what is G and what is F? F is just F. But G is dl by dq dot. I'm not fiddling around with this term. I'm only fiddling with this term here. And for this term, dl by dq dot plays the role of G. We have F dot times G. Okay, so let's put a red circle around the thing that I'm identifying as G, and a red circle around G over here. Okay, so what do I get then? For the second term alone, the second term becomes minus integral dt from t1 to t2 dt, and now f times g dot. That means, dot means d by dt. D by dt of the derivative of L with respect to q dot. A rather complicated looking thing. D by dt of the derivative of the Lagrangian with respect to q sub I dot times f sub I. Derivative, it's here. This is g dot. Right? D by dt of g. And instead of having f dot, we now have f. So now we can write both of these terms. Both the terms, the term coming from varying q a little bit and the term coming from varying q dot a little bit, as integrals with the arbitrary function f. Let's write the whole thing down now. This one came in with a minus sign. It's this term. And the first term was just dl by dq. F sub I. Well, this will do it. Integral dt. Whole thing gets integrated here. Again, I'll just remind you what it is. This is a term, the action changed because we changed q a little bit. This is the change in the action because we changed q dot a little bit. What about the contribution from the endpoints of the integral? Remember, there was another term which was f times g at the endpoints.
They all vanish.
Why do they vanish?
Up there at the top, you stipulated that you wanted those guys to.
We stipulated that the trajectory passed through the initial and final point. So that said that f should be 0 at the endpoints. And so there's no contribution here. Well, what have we calculated? We've calculated the change in the action with respect to alpha. Change in the action with respect to alpha. At alpha equals 0. We can now set alpha equal to 0. It doesn't matter. It doesn't even depend on alpha. What's the rule? The rule is that this should be equal to 0. That's the condition of minimizing the action with respect to alpha. So this should be equal to 0. Notice that the f's can be taken outside the bracket. Oh, you're probably aware that there should be a sum of I here. Each term in the sum is f sub I, multiplies f sub I. This has to be 0 for every possible function f sub I. All possible ways of deforming the trajectory. Why? Because we're looking for the trajectory with the minimum action. And so however we deform the trajectory, we should increase the action a little bit. So it follows then that this integral has to be 0 for every possible function. Well, what does that imply? That implies that the thing in the curly bracket here has to be identically 0. So what we've done is we've taken the condition of least action and we have converted it to a local statement at each point along the trajectory. At each point along the trajectory, we can get, incidentally, this is true for every combination of functions, f1, f2, f3, and so forth. That means that every one of these expressions has to be equal to 0. For each I, at every point in time, the L by dq minus d by dt of dl by dq dot has to be 0 all along the trajectory. This has the form of a local equation at each point on the trajectory. It's equivalent to the global statement that the action is minimum. Okay, now that this is, incidentally, this is called the Euler-Lagrange equation for the variational problem of minimizing the integral of L dt. This is called the Euler-Lagrange equation. Euler, not O-R, not like the football team, not that, but E-U-L-E-R, Euler. Euler-Lagrange variational equation. And this equation is the heart of all of classical physics. In fact, in a slightly different form, well, a related but more sophisticated form, it is also the heart of quantum mechanics in the form of the Feynman path integral. Every physics problem known to me, or every physical system known to me, probably known to anybody, can be formulated as an action principle with a Lagrangian. Okay. That doesn't only include mechanical systems, it includes systems of fields, gravitational fields, general relativity, string theory, everything has the form of a variational principle, meaning to say a principle of least action.
What does it say in English?
What does what say?
This final statement here of the Euler-Lagrange equation.
Well, I think the best way to, let's come back to what it says in English after we work out what it says in specific examples. Perhaps by the time we say some specific examples, we'll understand what it says. What does it say? What's it say? F equals ma. Is that English enough? So that's the next thing to do, is to show that in a couple of cases of interest, it really does produce the right equation of motion. Right? But in English, really what it is it's the equivalence between a global description of the trajectory and a local description. Right? The local description is a differential equation. It's a differential equation, as we'll see. We'll work out some examples, or it's a system of differential equations of the form f equals ma. Incidentally, just in terms of some lingo, some definitions.
I wonder if there's another way of looking at that just from looking at the equation.
Which equation?
Just looking at the math. You have a time derivative of the velocity derivative.
Yeah.
In equating that to the space derivative of the
Yeah.
object.
Yeah. You're asking, is there another way to say it?
Is that a way to say it?
Yeah. Yeah, the time derivative of the derivative Lagrangian with respect to a velocity, let's call it, is equal to the derivative Lagrangian with respect to the corresponding coordinate. All right. But I think the best thing to do, let's write it up here and then work it out for some examples to see how it works.
It's just that, space derivative means something to me, and, you know, the time derivative or velocity derivative means something that I can picture.
Say it again.
That term, just in sort of units analysis, is, you can think of derivatives as sort of vectors. And
Yes, and this,
so you
right.
have velocity giving you one component and the time derivative of that. So that's sort of pushing you forward along the trajectory.
Yep.
And the other one is sort of moving you.
Just something at the specific point.
Yeah.
Right. All right, let me give you some names. The quantity dl by dq sub I dot, notice that it depends on I, so it depends on which coordinate we're talking about. That has a name. It's called, first of all, it's got a symbol associated with it. It's usually called pi sub I. It's the derivative of the Lagrangian with respect to the velocity q sub I dot. So it's a component of something that's related to the derivative of Lagrangian with respect to a component of velocity, if you like. Anybody know what the name of this is? It's the momentum canonically conjugate to q, the q sub I. Or you can just say the momentum. The momentum component, which corresponds to the position component q sub I. If you think of the q's as a bunch of positions, then the pi sub i's are called the momenta. All right. Now, all right, so what does this say? This says d by dt of something that I'm calling a momentum is equal to dl by dq. How about this? Has this got a name? Yeah. The generalized force. So this is the, I'll just call it the momentum, but it's called the canonical momentum conjugate, or the momentum conjugate to q. Okay, momentum conjugate to q. For every q,
QI.
to qi, thank you. All right. On the other hand, dl by dqi is called the generalized force, or generalized component of the force. I won't bother writing component, you get the idea. So what this says is the derivative of some momentum is equal to some force. Sounds like F equals ma, and it is F equals ma. Let's try it out for a specific Lagrangian t minus u. Let's first do it for a single particle. One particle, mass m, for the moment, one direction of space, just the simplest possible problem, then t is equal to 1/2 the mass of the particle times x sub I dot squared. Just x squared. That's one coordinate. The simplest possibility. That's t, the kinetic energy. X dot is, of course, just velocity in disguise. Minus u of x. That's L. What is the q for this problem? I'm not using the language of q's at the moment. Q is, of course, just x. So I'm reserving x now for linear position along a line. But, of course, it is the q for this problem. Q is just a generalized term for any kind of coordinate. X is usually used when we're talking about rectilinear coordinates or Cartesian coordinates. All right, let's work out what Lagrange's equations say. What the Euler-Lagrange equations say. First of all, what is dl by d? Now it becomes dl by dx dot. This is the canonical momentum conjugate to x. Well, dl by dx dot here's x dot, the only place where x dot appears, is just equal to mx dot. The 2 goes away because we have x dot squared. And when we differentiate with respect to x dot, that just gives us mx dot. That is what we usually call the momentum, sometimes called p. Okay, so here's the language. When we're talking about ordinary coordinates along lines x, y, and z, we use the language x. For momenta, we use the language p. When we're talking about more generalized kind of coordinates, we use the language q and pi. But in this case, q is x and pi is p. What does Lagrange's equation say? It says d by dt of dl by dx dot, but that's mx dot, is equal, now, we can write this, let's, equals dl by dx. dl by dx is minus du by dx. The only place where x appears is in u. X dot appears here, x appears here. So this is just minus du by dx. This should be familiar. This is just F equals ma. Mass times x double dot is equal to minus du by dx. So we successfully reproduced Newton's equation for a particle with 1 degree of freedom moving along a line with a potential energy U. Notice that had I used for the Lagrangian plus here, I would have gotten the wrong sign in the force law here. So the energy, which we haven't talked about yet tonight very much, we'll talk about other times, but the energy, which is T plus U, is not the Lagrangian. The Lagrangian is T minus U. And the Lagrangian is not conserved. The Lagrangian is typically not a conserved quantity. As the particle moves along the orbit, in general, the Lagrangian will change. It's T plus U which doesn't change, but we have to come back to that. We want to derive that. We want to derive energy conservation from this rule here. But so far, we do have Lagrange's equations. Okay, now let's go forward a little bit to a many-particle system. For a many-particle system, all we have to do is, for each particle, let's have many particles and many coordinates for each particle. 3 coordinates for each particle, x, y, and z. Let's just call them x1, x2, and x3. But also, we have all of the particles. Let's lump them all together and call them x1 dot 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 down to xn, where n is 3 times the number of particles.
We could say 3n.
3n, but let's use capital N for the total number of x's. Now, each particle might have a different mass. So that means each x dot squared might have its own mass that goes along with it. Of course, they'll come in triplets. The mass of a particle doesn't depend on which way it's moving. But we can think a little more generally. We can imagine a slightly more general situation where every x dot squared goes with its own mass. This would be a mathematical, for a real physical particle, of course, the mass doesn't depend on which way it's moving. So in triples, they would come together with the same mass. That's all right. We can extend the notation a little bit and just write that the kinetic energy is the sum over all the coordinates of the appropriate mass for that coordinate times x sub I dot squared divided by 2. Now this I doesn't just mean 1, 2, and 3, meaning x, y, and z. And it doesn't just mean which particle we're talking about. It means the collection of all the different things which specify a particular coordinate, which particle as well as which direction. And then the potential energy, which is a function of where the particles are, it's a function of the positions of the particles, just becomes minus some potential which depends on all of the particles. I didn't have to change it, it's just minus u of x. U of x here means U of all of the coordinates. Now, in specific instances, you may have some particular special form, and we'll talk about the special forms that it can have. But in a general context, we can imagine a U which just depends on all of the positions of all the particles. Then what happens if we go through the same exercise coordinate by coordinate? Well, the L by the x sub I dot becomes m sub I times x sub I dot. We'll call that P sub I. This does no sum intended here, no summation intended here. So, if this is x, y, or z, this could be the x, y, or z component of a particular particle momentum, but we could also vary which particle we're talking about. And so this extends not only over the directions of space, but which particle we're talking about. There are 3n momenta and 3n positions. Each equation then takes the form of the time derivative of the momentum of a particular direction in a particular particle is equal to the force, the component of the force associated with a particular particle and the particular direction of space. Okay. This again is F equals ma. F equals ma for each particle and each direction of space. So, m sub I x sub I double dot is the u by the x sub I. The implication is that this must be very, very general. After all this is a collection of particles with force laws, the force laws happening to be just such to hold it together into an eraser. You're nothing but a collection of particles held together by forces. This is an extremely general system that we're talking about here, and it is definitely governed by a principle of least action, the principle of least action being gotten by taking taking kinetic energy minus the potential energy. So we see already that the principle of least action is general enough to cover just about every possible mechanical system we could think about, because every mechanical system we could think about we could imagine being made out of chunks of material which in turn are made of collections of particles held together by interatomic forces or whatever holds the system together. Let's do a couple of examples just to see how things work. Let's do an example of two particles on a line interacting with a force between them governed by a potential energy. All right, so we have two particles on a line. Particle 1 has coordinate x1, particle 2 has coordinate x2. Particle 1 has mass m1, particle 2 has mass m2. Now, there's also a potential energy function. The potential energy is a function of both coordinates. If there's a force between the two particles, and the two particles influence each other, then you would expect in general that the potential energy will depend on the position of both particles, maybe in some complicated way. Now I want to focus on a particular situation, and the particular situation is one which has what I'll call, or what everybody calls, translation invariance. Translation invariance means that for our purposes now, the Lagrangian, or let's say in particular the potential energy, would not change if you moved both particles together. In other words, it doesn't depend on where the particles are, it does depend on the distance between them. This assumption is equivalent to a symmetry. The symmetry being, I'll explain what I mean by a symmetry in a moment more generally, but the symmetry being translation symmetry. Nothing depends on where you put the origin of coordinates things only depend on the distance between particles, which is another way of saying that if you move the whole system, if you translate it, translation means moving it rigidly, everything being kept at the same distance, that in this case the Lagrangian would not change. The velocities don't change if you just take a particle moving with a given velocity. A given velocity means it moves a certain distance in a certain time. If you change both the initial position and the final position by the same amount, then the velocity doesn't change. In other words, if your car goes 1 mile in 10 seconds, wow, that's fast now. But you move it ahead by a certain distance, and you keep the velocity the same, then it's still going 1 mile. You know what I mean. Velocity itself doesn't depend on the choice of coordinates, on the choice of origin. Why? Well, let's think of x of t, and let's add a constant to x of t. Just add a constant to it. If you add a constant to it, it doesn't change the time derivative of x. So shifting everything by a constant amount would change none of the velocities. And if the potential energy only depends on the distance between them, then the potential energy doesn't change if you rigidly move everything. Under those circumstances, the Lagrangian has, or the system has a symmetry. It doesn't change if you move everything by the same amount. So specifically then, in that case, the Lagrangian for this two-particle system would be kinetic energy, m1 x1 dot squared divided by 2, plus m2 x2 dot squared divided by 2. Those are the kinetic energies. And then the potential energy minus, and the potential energy now is assumed to only depend on the distance between x1 and x2. So it only depends on x1 minus x2. Now, this would not be the case if there was a large lump of matter out here that happened to be exerting forces on both x1 and x2. Then the potential might also depend on how close you were to that lump of matter. It wouldn't just depend on the distance between them, but it would also depend on the distance to the big lump over here. But if the only system, if the system is a closed system containing only two parts, and if it's translation invariant, meaning to say everything stays the same if you shift everything, then the potential energy can only be a function of the distance between the 2 points, x1 minus x2. Actually, it doesn't have to be absolute value, but we could make it absolute value if we wanted. If we wanted it to be literally the distance between the 2 points, then we would make it absolute value. But for my purposes right now, it's good enough that it's just a function of the separation, the x1 minus x2. That's good enough. That's translation invariant. That means that if we were to add a constant to each x, the same constant to each x, nothing would change. The velocities wouldn't change because the velocity doesn't depend on c, and x1 minus x2 wouldn't change because the constant translation would cancel out. All right, so this is a symmetry. This is the case of translation symmetry. Let's work out now Lagrange's equations. There's an equation for x1, and there's an equation for x2. The equation for x1 is d by dt, let's write out, d by dt of partial of L with respect to x1 dot equals partial of L with respect to x1. All right, d by dt of partial of L with respect to x1 dot, that's just ma for the first particle, right? That's just d by dt of p1. P1 by dt. P1 being the momentum of particle 1. The L by the x1 dot is just mx1 dot, that's the momentum, And so the equation for the first particle starts with dp1 by dt is equal to dl by dx1. All right? The only thing that depends on x1 is u, and so that becomes is equal to minus du by dx1. What about the second particle? That's particle number 1. Let's do particle number 2 now. dp2 by dt, that just comes from here. That's going to equal minus du by dx2. What's the relation between du by dx1 and du by dx2? They're equal and opposite. If a thing only depends on the difference of two variables like this, then the derivative, well, let's look at it. The derivative of u with respect to x1 is just the derivative of u with respect to the argument. Is it obvious to everybody that the derivative with respect to x2 is minus the derivative with respect to x1? If it's obvious to everyone, I won't explain it. Okay. Okay. All right. So let's do it then. We have a function which only depends on x1 minus x2. Now let's just call this variable x1 minus x2. Let's give it a name. Let's call it x. So u is only a function of x. No, let's not call it x. Let's call it d for difference. D for difference. So u is a function of d. D is x1 minus x2. All right, let's calculate, first of all, the derivative of u with respect to x1 by the chain rule. The derivative of u with respect to x1 is the derivative of u with respect to d. Remember, u is really only a function of d, times the derivative of d with respect to x1. What's the derivative of d? This is d, x1 minus x2. d equals x1 minus x2. What's the derivative of d with respect to x1?
1.
1. So this is just du by dd. What's the derivative of u with respect to x2? That's du by dd times the change in d when you change x2. What's the change in u when you change x2? What's the change in d when you change x2? Minus 1. The derivative of d with respect to x2 is minus 1. So, there's a minus sign between them. The derivative with respect to one variable is minus the derivative with respect to the other variable. That's as a consequence of the fact that it only depends on the difference between them. Well, the implication seems to be Newton's law of action and reaction, and it is. The fact or the assumption that the potential energy only depends on the distance between them, or the difference between the two variables, that it's translation invariant, that there's a translation symmetry, that's equivalent to the statement that the force on particle 1 is minus the force on particle 2. What's the net result? The net result is momentum conservation. If you add these two equations to find dp total, p1 plus p2 by dt, then the forces on the right-hand side will cancel, just as they do, just as Newton assumed that they would. So what we find from this is that momentum conservation for this simple system here is a consequence of translation invariance. It's a consequence of translation invariance, number one, and number two, the form of the equations and the fact that they derive from the principle of the least action. We're going to explore this more thoroughly. So far, this is just an example. And it's an example of the relationship. This is really, really important. This is maybe the most important thing that you can learn tonight, or that you could learn about theoretical physics practically, is the connection between symmetries and conservation laws. Here's the first example of the relation between a symmetry, translation invariance in space, and a conservation law, which is the conservation of momentum. The symmetry says that U only depends on x1 minus x2. From that, it follows that the force on particle 1 is minus the force on particle 2, and from that follows conservation of momentum. Conservation of linear momentum, we'll call it. So this is the first example, and we'll see more of them, of conservation laws and their relationships to symmetries. As I said, this is a very, very deep underlying theme of physics, of theoretical physics, that every symmetry has associated with it a conservation law. What does a symmetry mean? A symmetry means an active operation that you can do on the system, for example, translating it, which does not change the Lagrangian, which does not change the value of the Lagrangian, or better yet, the value of the action. If the action of a system does not change when you do a transformation of some type, in this case, just moving everything to the right by a fixed amount, that is a symmetry of the particular action that we're talking about. Every time the action has a symmetry, there is associated with it a conservation law. This is the simplest example of that, and the first of many examples that I hope we'll see over the next however long we pursue this. Question?
There's another symmetry there that's the same as translation, which is inversions.
Ah, yes. Yes, very good. In particular, there would be an inversion symmetry if this were a function only of the absolute value. Yeah. Okay. In classical mechanics, that's called a discrete symmetry. A continuous symmetry is one that you can imagine doing a little bit or a lot. We'll talk about this difference between discrete symmetries and continuous symmetries. But a discrete symmetry is one that depends on a parameter that can be very small, just a very small shift, or very big, or that you could build up the big shifts out of a lot of little small shifts. That's called a continuous symmetry. A discrete symmetry is an operation like interchanging two things, which only has a discrete form. It's either one way or the other, and there's nothing interpolating between them. In classical mechanics, discrete symmetries don't generate interesting conservation laws. In quantum mechanics, they do. So, but that's for a later discussion. So you're right, it does have another symmetry, in particular if we say this is a function of absolute of x1 minus x2. This wouldn't have much oomph, much implication in classical mechanics. It does have implication in quantum mechanics, implication of a conservation law. Okay, so we just did conservation of momentum for a simple case. Let's do a couple of more mechanical cases, a couple more mechanical systems to get the feel for this. Let's do a problem in which a particle moves in 2 dimensions. Particle moving near the surface of the Earth. Here's the surface of the Earth. Here's our particle right over here. Of course, it has 3 coordinates associated with it, but let's just take 2 coordinates, x and y. X goes this way, y goes vertically upward. The particle is described by 2 coordinates. There are 2 q's now, not because there are 2 particles, but because there are 2 directions of space, x and y. Okay. The kinetic energy is 1/2 m x dot squared plus 1/2 m y dot squared. I have assumed that the mass does not depend on which direction the particle is moving. We could imagine some sort of nutty particle which had a larger mass with respect to vertical motion than horizontal motion, but I'm not doing that now. And then what about the potential energy? All right, this is the gravitational potential energy that I'm talking about. The the gravitation, in case I haven't said it before, I will tell you now, the gravitational potential energy of an object near the surface of the Earth, this is not in a situation where we're far from the surface of the Earth, but near the surface of the Earth, is just proportional to the height, to the elevation. Right? So, we subtract the potential energy. The potential energy is equal to the height of the particle, y. It's proportional to its mass. The heavier the particle, the more potential energy it has when you lift it. And it's proportional to the acceleration of gravity, g, 10 meters per second per second. Little g is 10 in metric units. And it's just the strength of the Earth's gravitational field near the surface of the Earth. Okay, let's ask, what is the force on a particle? The force on the particle has no x component because du by dx is equal to 0. Du by dy is equal to mg, but the force is minus that, so minus du by dy is minus mg. And the minus sign represents the fact that the force is downward when we take the y-axis to be pointing upward. So it's accelerated downward. All right, so let's add now, or subtract, as the case may be, the potential energy minus mgy. What kind of symmetry does this problem have? Well, it has translation symmetry along the x-axis. If I change x by a constant, it doesn't change x dot. And since the potential energy doesn't depend on x, the Lagrangian, this is Lagrangian, the Lagrangian is translation invariant along the x-axis. It has x translation. How about y translation invariance? Does it have y translation invariance? No.
Small y.
Because of the y over here. Did you ask me why?
No, for small y.
For small y. Why?
Yeah.
Why for small y?
Who saw it first?
No.
If you stay close to the surface, it doesn't change much.
Who's the president of China? Excuse me.
I think he's thinking of for small dy, the potential doesn't change very much or something.
The small y, the small,
I don't know.
I don't know either. When you change y, the Lagrangian changes, right, because of the y that's here. Now notice, incidentally, let me point something else out. We could add a constant. This is something I should have pointed out a while ago. You can always add a constant to the potential energy at no cost. It changes none of the physics. Now that constant has to be treated as a true constant throughout the problem. It doesn't change anything because it doesn't change the force, if you add a constant, it doesn't change any of the derivatives of u, and so it doesn't change any of the forces. It resets the zero of potential energy, but there's no physical consequence of adding a constant to potential energy. So it doesn't matter where you measure the altitude from, whether it's sea level or whether it's 10 meters above sea level, or so forth. But if you change y, you change u. All right, so with that logic, we should find one conservation law, not two. We should find one conservation law associated with x and not the corresponding conservation law with respect to y, because there's only one symmetry. And in fact, if we work out the equations of motion will be dl by dx dot is mx dot, d by dt of that, that's called ma, mass times acceleration, and that's equal to 0. Why 0? Because u doesn't depend on x. This is just conservation of the x component of momentum. So the x component of momentum is conserved, but the y component of momentum, d by dt of my dot, that's the time derivative of the y component of momentum, is the derivative of u with respect to y. Derivative of minus u with respect to y. So that's equal to minus mg. Minus mg, du by dy is minus mg, or minus du by dy is minus mg. All right, so what is this equation? This just tells me that the vertical acceleration is proportional to the force of gravity, or that the acceleration is equal to the acceleration of gravity. We can cancel out the m's here. But notice, the important thing is that there is no conservation of y momentum, of the y component of momentum. And that's associated with the fact that there is no symmetry associated with translation in the y direction. I'm going to do one more example of the relationship, in particular the relationship between symmetries and conservation laws, but also it's an example in which I won't use rectangular coordinates.
May I make an observation here which may be
No.
obvious or
Yes,
maybe
of course.
not? But which the equation that you've written for Lagrangian by no accident for this falling body is exactly the equation you would get if you did this with freshman classical physics in a mechanics problem for a falling body.
Well, wait, you would never write this down in classical physics.
No, I'm saying you would say that there is conservation of energy, the fact that potential energy and the kinetic energy remain constant. So it's, I just wanted to point that out, that it's reformulation is something we probably have already seen.
The reason, so far I haven't even talked about, in this context, conservation of energy.
Yeah.
We will talk about it, and you'll be perfectly right. We'll find that in this structure, there's a conservation not of kinetic energy minus potential energy, but kinetic energy plus potential energy. So it's going to require an extra step to see that the energy is conserved. And we're going to want to ask the question, if energy is conserved, is it also conserved because of some symmetry? And if so, what symmetry? So we want to formulate our laws of, the basic law of physics now is that symmetries equal conservation laws. And we're going to want to see that, and that follows from the form of Lagrange's equations. But it's little feet for little steps for little feet. The principle of least action does not really depend on the coordinates that you use to describe the particle. Whatever coordinates you use, you could use polar coordinates, you could use rectangular coordinates, you could use parabolic coordinates, you could use some screwball coordinates with curved, fancy curved axes and so forth. You can always...
Why are those screwball? They seem perfect. Work coordinates are perfectly normal.
Normal coordinates with curved axes and so forth. Use any coordinates you like. You can rewrite the expression for the kinetic energy. You can rewrite the expression for the potential energy. It may look more complicated in other coordinates, but you can rewrite the expression for kinetic energy, potential energy, and Lagrangian, and you can rewrite the expression for the action. The action may look more complicated in terms of other coordinates, but it will still be the same good old action. It will depend on the trajectory and give you the same answer that you would have gotten in rectangular coordinates if you rewrite it correctly. The fact that the action is minimized for the correct trajectory is a statement that doesn't depend on what coordinates you use. So the principle of least action is a principle that is coordinate independent. It doesn't depend on the specific coordinates, and therefore you can apply it to any set of coordinates you use to describe a system. I'm going to show you how you would do it for polar coordinates if we were talking about a particle again. Let's take the case of a particle moving in a plane. And now instead of describing it by x and y, let's describe it by r and theta. Distance from the origin r and angle relative to the horizontal theta. We have to write the Lagrangian. Then we'll write Lagrange's equations. It's a system with two coordinates, r and theta. And a trajectory will now consist of an r of t and a theta of t. In other words, at every instant of time, the distance from the origin and the angle, that determines the trajectory of the particle. Okay, let's work out the kinetic energy first. The kinetic energy is 1/2 mv squared. So what we have to do is we have to calculate the magnitude of the velocity. To do that, let's temporarily set up some coordinates at this point over here, at the point of the particle, where one axis is along r and the other axis points in what I'll call the theta direction, sort of along the angular direction. But temporarily, for the moment, let's just think of them as Cartesian coordinates, except erected right at this point. Then the velocity has two components. One of them is the component along r, and you will not be surprised, I will not work this out for you, but you won't be surprised, I think, if I tell you that the component of velocity along r, all right, is v sub r, velocity along the r direction is just r dot. If r is changing, then there's a component of velocity along r, and it's just the r dot. What about the component of velocity in the perpendicular direction? How big is it? You might think it's just theta dot. This is v along the other axis. I don't want to call it v theta, I'm just going to call it v along the perpendicular axis, perpendicular to r. How big is that? Right. It's not theta dot, but it's r theta dot. How do you see that? Well, supposing the particle is near the origin over here, and you change theta a little bit per unit time, then it moves a little and it has a certain velocity. Suppose you change the angle by the same amount, but the distance of the particle is far away. Then it moves a lot more. So the further out you are, for a given theta dot, the further out you are, the faster you're moving, right? The tips of my fingers is moving faster than my elbow. And in fact, the velocity is proportional to how far away you are. But it's also proportional to theta dot, because if theta dot was 0, if there was no change in the angle, you would have no component of velocity along that direction. So these are the two components of velocity. And the kinetic energy is 1/2 m times the r component of the velocity squared, r dot squared, plus 1/2 m times v perpendicular squared, which is r squared theta dot squared. This is the kinetic energy. Now let's invent the potential energy. I'm going to invent a special kind of potential energy, which is called the central force. Central force means that the potential energy only depends on distance.
Is there a square there?
It should be R squared.
R dot squared, right? First term.
Sorry, r dot squared, thank you. R dot squared, mv squared. So there's 1/2 mr dot squared and 1/2 mr squared times theta dot squared. Now let's introduce a potential energy. And let's make the potential energy that only depend on r, only depend on distance. That's a special case, but it's a special case with symmetry. What's the symmetry that's involved if I say that the potential energy only depends on distance? Rotational symmetry. What that would say is that nothing changes if I rotate everything. If the potential energy only depends on distance, only depends on distance, that means the potential energy does not change if I rotate the position of the particle, or if I rotate the axes. If I just physically take the particle and rotate it without stretching r, then the potential energy doesn't change if the potential energy only depends on r.
You have to check that the T term doesn't, the kinetic energy doesn't depend
Yes,
on R as well.
but it doesn't depend on theta.
On theta.
Yeah, but it doesn't. It doesn't. It depends only on theta dot, so if we change all thetas by the same amount, yeah, that's correct. We have to check that. But as you can see, because it only depends on theta dot and not theta explicitly, then if I shift all thetas, In other words, I say theta, you know what I mean. Okay. So then we have minus u of r. Minus u of r. Let's work out now the Lagrange equations of motion. The q's are r and theta. So all we have to work out is, first of all, for r, let's start with r. Partial of L with respect to r dot, incidentally, this is L. L is kinetic minus potential. Partial of L with respect to r dot is mr dot. That's also equal to the momentum conjugate to r. It's just a radial component of momentum. M r dot, or m times the velocity in the r direction. Not surprisingly, that's the radial component of a linear momentum. All right. Then Lagrange's equations become d by dt of this, which is d by dt of mr dot, it's also known as mr double dot, the radial component of acceleration, is equal to minus du by dr. Obviously, minus du by dr is the radial component of force. This is just a radial component of F equals ma. The mass times the second derivative of r is du by dr. Notice that the radial component of the momentum is not conserved. Okay? We can write this as d by dt of the radial component of momentum, not equal to 0, but it's equal to minus du by dr. So there is no conservation of radial momentum. Let's look at the angular equation of motion now. The angular equation of motion, the equation of motion for theta. Same deal. Just think of theta as a generalized coordinate. Partial of L with respect to theta dot, that's mr squared theta dot. What's its name? What's the name for that object? The canonical momentum conjugate to theta. What's another name for it? Angular momentum. All it is angular momentum. But we see now angular momentum arising out of the same pattern. dl, this is dl by d theta dot. Same pattern. Derivative of L with respect to q dot is the momentum conjugate to q. dl by dr dot, momentum conjugate to r. dl by d theta dot, momentum conjugate to theta. Now what is the equation of motion for theta? It's d by dt of this, d by dt of mr squared theta dot is equal to what?
0.
0 in this case, because u doesn't depend on theta, by assumption. d by dt of something equals 0, that says that that something doesn't change. So this is an equation of conservation. It's conservation of mr squared theta dot, or conservation of angular momentum. When the force, or when the potential energy doesn't depend on angle, then angular momentum is conserved. It's usually called L, incidentally. This is usually called L. So it says that L is conserved. In fact, that allows us, that gives us a good clue about the nature of the motion of the system. If L is conserved, let's just see what that says. It says that mr squared theta dot doesn't change. So it says that mr squared theta dot is equal to a constant. It doesn't change with time. It's whatever it was when you began. However you began the motion, the angular momentum doesn't change. Well, you can solve this and write that theta dot is equal to the constant over mr squared. So you see what happens as r goes in and out for whatever reason. As R perhaps either oscillates or it gets bigger or it gets smaller, theta dot changes to compensate. This is just the spinning ice skater effect. As R gets smaller, theta dot gets bigger. Okay, it's the conservation of angular momentum. But you see, it arises once again from a symmetry. The symmetry in this case being rotational invariance. Rotational invariance, angular momentum conservation. Translation invariance, linear conservation of momentum. That's the pattern.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.